suppose there's this complex number then. So a cube root over the other side. We're going to use DeMoivres Theorem, so we're going to use mod argument form, which we did yesterday. I think we also used 1 to start off yesterday, but we did the 4th root. What's the angle here? Yeah, so we're dealing with 1, so that's here, just right on the axis. So 0 plus I sine 0. Now, yesterday I did the classic application, which was do like 1/3 on or 1/4 on the other side and stuff like that. I'm going to show you a different way to do it now. I'm going to apply DeMoivres theorem to this side. Oh. Yeah. It's actually going to be easier. It's going to be easier when you're dealing with the angle going round. Okay, does that make sense? Z cubed. Oh man, you need to. You can move closer if you need, Abby.
He's not, but it's not going to move forward.
I know, yeah. Okay, Abby, too much like a sensible decision. Okay. So we're looking for a bunch of solutions. How many solutions do you think we're going to get here?
3.
3 makes sense. 2? 2 makes sense. 2 makes sense in the real world anyway.
At least 1.
It's definitely going to be
Or
3.
does it? Oh, it's not squared. Yeah.
Well, then definitely
1 makes sense.
We need to find the 3rd root. So there's going to be 3. Well, there's going to be 4 or something. There's going to be as many as you want. I don't know.
Okay. So you can see that the left-hand side equals the right-hand side here. So we can make some assumptions that the modulus would equal the modulus. Yes? So the r cubed would equal 1. So mod equals mod. So r cubed is equal to 1. So the modulus of all the answers would have to be also, well, the cube root of 1, which is, cube root of 1, which is 1. So the modulus of all the answers. When I say all the answers, we'll discuss how we form all the answers. We definitely get 1. We know 1 anyway. Now we look at the argument part, the angles part. So I'll just rewrite this without the mods. So this must equal this. Yep. Let's take the real and let it equal the real. So the real wouldn't have the i's with it. That's the cosine bits. And the imaginary equal the imaginary. Now you actually wouldn't do this every time. I'm just going to show you why you don't do it every time in a second. Okay. So we're going to look at the shape of these graphs. The shape of a sine graph, in general, the shape of a sine graph starts here and it repeats, or sorry, it is 0 how often?
Per period? Or like...
Well, how often does it hit 0? Here, yeah, okay, the period of, it's not a period, but how often, what's the distance between these two? So 0 and the next one is at pi, and the next one's at 2 pi, the next one's at 3 pi, and going backwards it would be negative pi. And does that make sense? Every pi it would hit that 0 again.
Yeah.
What about the cosine one?
Isn't that half pi?
It would be half pi, then 3 pi over 2, then 5 pi over 2.
Okay. What solution are we looking for here? So the reason I'm looking for 0 here is because sine 0 is 0. Sine 0 is 0.
Cosine 0 is 1.
So cosine 0 is 1. So how often is this solution? Oh, sorry, it should be right at the start here. How often is this solution?
Would that happen to also be pi and 2 pi?
No, because every second one is going to be minus 1.
Isn't it half?
No, it's 2 pi.
How
0.
often does it equal 1?
How often does it equal 1? Because cosine 0 is 1.
Yeah.
So every 2 pi. All right. You wouldn't normally do this, but I'm just showing you that sine gives you too many solutions. Because it has to work for both. Because it's the same angle. Cosine is the one you need to work with. Because it gives only every second solution of sine. Sine gives a bunch solutions. Half of them won't work also for cosine. So that's why we will work with only the cosine when we go to solve these. So you'll just ignore the sine and you'll just go with cosine to solve. That's the reason why. Sine has too many. Okay, let's go back to then the problem. We're just going to, it gives us the right solutions, but it gives us too many solutions. This one, so we just stick with this side. Okay, so we could say that 3 theta then is equal to 0. Yes? Okay? But because of the nature of cosine, we just saw it, that there's a bunch of times. Or if you do this, a bunch of times where that's going to be true. Yeah? Every, how many times?
2 pi.
2 pi. Okay? So we don't say 2 pi though, because that would only be one more time. We use that general solution that we had the other. They do use k. 2k pi. Yeah. So if k is 1, it's 2 pi. If k is 2, it's 4 pi. If k is minus 1, it goes backwards. Okay? So this gives us all the solutions. But we want theta, so it'll be 0, well, over 3 plus 2k pi all over 3, something like that, yeah? Okay?
0 plus, well, 2k pi into 0? Well, if we assume that it's...
Well, yeah, okay.
So we assume that k is for all...
The answer won't always be 0 here. So just making sure we know the 0 wouldn't really matter. You could definitely simplify that straight down to this in this case. Okay, this will give us all solutions. We just have to find them now. Which ones, what do we put in for k?
Integers?
Integers, yeah. Which ones? What's our angle, what must our angle be between? Our principal argument is always between what?
0. Negative pi and 9.
0 and pi and 0 and negative pi. So from negative pi up to pi. So we'll only get solutions that give from negative pi up to pi. So we don't go 0, we don't go fully around, we go this way and then that way. And might make sense now, but we'll look at how we form our answers. So we have a modulus always of 1 and an argument in this form. So we'll put it back into mod arg form. Our general solution is 1 cos 2k pi over 3 plus I sine 2k pi over 3. Now we're going to start subbing in for k. Mm-hmm. Yeah. What's the first thing we sub in? I think, Philaine, you've done this already, Philaine, have you?
I really don't mean to.
No, it's okay. It's great. Yeah, you. 0. Okay. K is 0.
By induction?
No, it's not proof by.
What's an induction again?
No, proof by induction is like a logical series of
I
steps.
know what proofs are, I don't remember what induction is. With K, and then
Yeah, and k plus 1.
This is like K and then K plus 1.
K plus 1, yeah, and all that. And then, right, you've done that already, right? We'll probably go over that again. Okay, when k is 0, so this is like the original case, when k is 0, what do we get?
0.
That's our 0 case. That's the one we already know. So we're going to call Z1, this first one we find, this first root we find, which is 1 cosine 0 plus I sine 0, because multiplying by 0 will lead with 0. What's that?
Cos 0 is 1.
I'm actually going to put it over here.
Sine 0, so it's just
Cos 0 is 1, so it's just
1 plus I? Or just
the sine 0 is 0,
yes.
so it's just 1. 1 plus 0.
It's the number we're looking for.
Look at that. We went all the way from the cube root of 1, and we got 1. Yay! Job done.
We love math.
Yeah, we love math, exactly. Where does that sit on our real and imaginary axis? Here. Here. Shockingly.
Yeah, wow.
Right, we kind of knew that anyway. Right, it's 1. All right, where do we go next? We want to find Z2.
K equals 1.
Let's let k equal 1 now. See what the next one might be going this way. It's just going to add more to the angle. So that's still the modulus is 1. The cosine now is 2 pi over 3 plus I sine 2 pi over 3. Where did the 2 pi over 3 come from all of a sudden? K is just 1. K is just 1. Okay, what is that as a Cartesian form? So we can, okay. Yeah, okay, so you notice this is in this quadrant. Pi over 3 is there, so negative half. Yeah. It's negative a half plus I root 3 over 2. So we have to be,
Is that one of the roots?
that's one of the solutions, yeah. So that's negative a half plus I root 3 over 2. So it's sort of like here.
So does it matter if you put the I in front or behind it?
No, not really, no. Yeah, I just like, when there's a square root, I like to put it to show that the I is not under the square root. Okay, next solution. The logical step here is to go K what? 2. Let's see what that gives us.
Oh.
When I go K2, what angle am I going to get?
4 pi by 3.
What's wrong with that?
It's past our border.
It's past our border. So we got to go backwards. Did we follow that? I'm not going to go K2 because I see that that's going to be 4 pi over 3. And we just said we just go up to pi, which is 3 pi over 3. So 4 pi over 3 is too far. So I'm going to go back. Kind of oscillate between 0 and then the closest ones to 0 are 1 and minus 1. Next closest are 2. Do minus 1 because 2 is going to give us 4 pi over 3, which is past 180 degrees, which is past where we want to go. It'll be in the same spot, but it'll have the wrong argument. It won't be the principal one.
So minus 2 pi.
All right, yeah, so we got minus 1 in here, so that's going to be cos minus 2 pi over 3 plus I sine minus 2 pi over 3.
1 over 2 and minus 3 over 2. You are correct.
It's going to
No, it's going to be the 4 pi.
it's going to be minus
Minus a half.
yeah
Minus root.
minus a half minus I root 3 over 2. That's from this. You need to get really good at those trigonometry. Get in. I think so.
Yeah, I'll take the other quadrant, why wouldn't I?
Third quadrant, yeah. Here.
Yeah, I see the bottom left of my brain says 4 for some reason.
Okay, around there. What can we say about these three complex numbers then?
These 3 are just 3 cube solutions.
Okay, they're just the solutions. Yeah. They would cube. Each one should cube to be 1. Does that make sense geometrically looking at them?
No.
No. Oh, right. Okay. So what's the modulus of each one of these? I haven't written it in, but the modulus is that's a distance of 1, and you can work it out if you want. That's definitely a distance of 1, and that's definitely should be a distance of 1. Should be a distance of 1 because we said it. Okay. What's the angle here of this one?
2 pi over 3.
2 pi over 3. When you cube a complex number, you end up multiplying by 3, so you end up. So that's it once, twice, 3 times.
Yeah, and then it moves back around.
So it ends up here.
Yeah.
Does this one work then?
It will go the other way around.
Yes, it's going once, twice, 3 times. It does end up here. So remember when you're multiplying a complex number, or you're cubing a complex number, you 3 times the argument. So there's 3 roots. Are they spread out equidistant around it?
Yeah.
Yeah.
All by a distance of, what is 360 over?
So they all have the same.
It should all be one way.
They all have the same modulus, and they're all equally spaced around the circle. So if you had something with
So the modulus argument,
z to the power of 6,
there would be 6 spaces,
they should be equally spaced 6 times around the circle.
which would just give you the angle next to them. Right?
The argument might not always be just divide 2 pi by 6.
It would all be based on
Depends on where the first one is. So if the first one's like a small angle, then
you have to account.
there might be one here.
That makes sense.
Also notice the symmetry. One is the conjugate of the other here. Because with a certain repeated multiplication, conjugates would end up cancelling and stuff like that. Maybe you're thinking about that. Maybe not. Okay, did that a bit slow. It's not, we did some extra work there of Let's do it one faster, actually harder, but faster. Let's do, which one do I want to do? Z to the power of 6 equals negative 64. So we're going to do another one that's not, it doesn't have a, this is a real number on this side, not a complex number. And then the last one we'll do is a complex number on this side.
Real number, but not one that you normally get with real roots,
No, exactly, yeah.
which means they're all complex.
Okay. So let's try and do this one a little bit faster. We'll leave this up as a reference point. This I can leave for the start of it. We want to try and get there a little bit quicker than we got the last time. So step 1, we're looking over here, we've written it like this. Solve this now this time. So let's turn this into polar form.